Hi. I want to talk about 2.1 dot product. Um, I will quickly go through some concepts. The first definition is I want to talk about is a dot product of points. So if we define dot product of points, so we need to notice this point is not a vector. We'll compare the dot product of vector later. So if we have point P and Q, then the dot product will be the sum of Pi and Qi. For comparison, there is also dot product of two tangent vector. So dot product of two tangent vector, which is a VP and a WP. So these two tangent vectors should be at the same point. So inherent from the dot product of points. So we can think about the vector part of a tangent vector. It's something like a point. So we can directly use V and W. And the V and W, we can write it also three coordinate form. So next thing is important, which is this section will we call it the frame of P. So the frame of P, I should say is at P. Is a orthonormal basis. This is very important. We should know we might know it's from linear algebra. So this is also orthonormal unit vector. So it just to say it's also normal basis. Also normal basis. So also normal basis does not have to be x, y, and z. It could be any direction, as long as it's a e1, e2, e3. Their norm is equal to 1, and they are pairwisely perpendicular. So that should be also normal basis. The perpendicular is defined as if ei times ej, the dot product of ei and ej equals 1, then we say these two vectors are also parentheses perpendicular. Sorry. So then what we need to say is a very important theorem, which is how can we express any vector as a linear combination of the frame of its frame. So this theorem is very important. Actually, any vector is just the vector, the dot product of the vector on each frame times the corresponding vector. Then we will get, I can write it in a simple case. Yeah, this will be easier for us. So how do we prove this? Because we know, what we know is E1, E2, E3 are three orthonormal bases that they form three-dimensional. Form three-dimensional, and this is the entire dimensional space as we study. So this is isomorphic to R3. It basically means any vector in R3 we can express using E1, E2, E3. So there must be some linear combination. So the rest thing is we want to prove EI equals VI dot product EI. So how to prove this? We can use this fact. EI times EJ equals, because we know what we know is suppose we can express in this way, then what we have is like this. Then this is just the canonical delta of ij. Then finally we're only left cj, right? So this will get okay. So we prove this theorem, and this theorem have a special case, which is what we exactly studied in the first chapter, this formula. And so we just know this. It's also orthonormal basis, but this is just like XYZ axis. So this is a natural coordinate. Okay. And using this, we can easily to derive the dot product of two vector. So we notice so the rest thing is just to put them together. So what we have is canonical delta ij. Then I and j must be equal, otherwise it will be 0. So this is exactly what we found for the formula. So this is very important when we do some problem in the exercises. So this is basically my presentation. Yeah, thank you.